First of all, I should say that, of course, this conference is in honor of Toshiyuki Kobayashi, who I first met just over 30 years ago, it turns out, at a conference in Massachusetts. That's correct, isn't it? Yeah, probably. You don't remember. Okay, and I thought that I was quite good at table tennis. And I found this guy at the conference that I could play table tennis with, so I did. And I was I was very pleased to find that I could hold my own against Toshi. And so we played a few games, and then I realized a bit later that he was using his right hand to write with. And so I said, "But you play left-handed table tennis." He remembers, yeah. And he agreed that he played table tennis left-handed whilst he was playing me. But normally, of course, he would play table tennis with his right hand. So he has many skills. Now, okay, now if you look at the abstract for this talk, I've kept the title, some parabolic geometry, but the abstract is almost totally incorrect. The thing that is correct is the last sentence, which says, hopefully with some original contribution at the end, it says. Okay, so of course what I was planning to do was give you some sort of general spiel about parabolic geometry, what it is and so on, and have an example at the end. But the example sort of took over. So I'm going to tell you about the example first, and probably that's all I'm going to tell you about. And we'll pick up what parabolic geometry actually is as a byproduct of discussing this example. Okay? So this talk is in differential geometry. And first of all, I'd like to just establish some notation for Riemannian differential geometry. In particular, talk about Riemannian geodesics. Okay, so all of this discussion is local, but I'm going to start on, let's say, a smooth manifold, M, and we're going to have an oriented smooth curve in this manifold. And first of all, I'd like to tell you what it means for this curve to be a geodesic in the presence of a metric. Okay, so a good way of setting this up is you start with a metric, and by the way, when I write things with indices on, like GAB, I'm not referring to something in local coordinates. It's a reminder that if you do express things in local coordinates, it has a couple of indices on, like that. Okay, and then there's the connection here, which takes some tensor, any tensor you like, and differentiates it, and that's got an index on to indicate that it's the answer is in a one form with coefficients in the bundle you first started with. Okay, so this notation is officially called Penrose's abstract index notation. So it has nothing to do with actual coordinates. Anyway, so that being said, if you've got a metric and an oriented smooth curve, you can talk about the tangent vector along that curve. That I'm going to denote by U and normalize it so that it's pointing in the direction of the orientation. And it's a unit tangent vector. And then this gadget here is the directional derivative along this curve. And you can easily check, take any tensor field you like, restrict it to the curve, apply this differential operator. It only sees the values of the tensor along that curve, even though, of course, as I've written it, you have to differentiate it in all directions first and then restrict it to the... So this repeated index, UA, grad A, is a standard trick in mathematical physics called the Einstein summation convention. So I'm just contracting the vector field into this one form. Okay, now of course if you have a Riemannian metric, there's no real distinction between tangent vectors and cotangent vectors, or one forms of vector fields. So if I just lower the index like that, that is a one form which is just as good as the unit tangent vector. And then if you differentiate that thing again, you get the acceleration, which again I'm going to think of as being a one form. So this is the acceleration, and then to say that you have a, just wait while I think, to say that you have, not yet, it's getting there. Oh, I don't know. It's very nice. I don't. Everybody will go to sleep. That's the problem. I mean, I don't mind, but anyway. So to say that you have zero acceleration is, of course, exactly to say that you have a geodesic. So this is a way of writing geodesics, okay? Of deciding what geodesics are. Okay, you all know this. If I start with this round sphere, for example, you can figure out what the geodesics are, and they are the great circles. Okay, and I should point out right away that when you're talking about geodesics like this, as I've defined them, they come equipped with a parameterization because I've got a metric. I can talk about the arc length along this curve. But for this talk, actually, we won't be too much concerned about how long it takes to get around this sphere or anything like that. We're just concerned about where geodesics actually go. It's like when you go to the optometrist or optician to get yourself a new pair of glasses or something, the optician has very complicated and sophisticated machinery which can measure where light goes in your eye and how it interacts with glasses. But they cannot measure the speed of light. Right? They only measure where it goes. So this is my viewpoint on geodesics and other special curves which occur in manifolds. Okay, so these are the geodesics on the round sphere. They are the great circles. Right, now a fundamental example of, I haven't told you what parabolic geometry is, but a fundamental example is conformal differential geometry. Conformal differential geometry is concerned with, well, in the Riemannian setting, concerned with picking a Riemannian metric and figuring out things which are actually invariant if you change the metric in the following way. So here's our original metric, GAB. Here's an arbitrary smooth positive function. If I multiply this metric by, for convenience, the square of that function, that's just a matter of convention, but it's convenient, then you get a new metric. And of course, the thing that you can do with this new metric, which is exactly the same as what you do with the old metric, is measure angles. Right? So you've got a couple of vectors. Right? The normal formula for the cosine of the angle between them doesn't depend on the metric, only the metric up to scale. And you can freely change this scale from point to point. So conformal differential geometry is concerned with the geometry that you get when you allow Riemannian metrics to change in this way. And geodesics are not conformally invariant. Okay, now that's if you know about the sphere, you know there are conformal transformations on the sphere which, for example, just move everything away from the South Pole and concentrate it on the North Pole. If you take the equator, that will move into a circle, but it won't move into a great circle. And you can see this in the formula for how these things transform. Right, so every time you have a new metric, g hat, I write the new gadget that you obtain from that with a little hat over it. So this is the new acceleration. And you can see the acceleration has changed. And in particular, if you start with something which has zero acceleration, there's no way that this is going to be remain zero, unless, of course, you start with a constant rescaling, in which case this thing which controls how things changes, this important one form, which is the logarithmic derivative of omega, is zero. Okay, so otherwise, there's this gadget here, this one form, upsilon sub a, which controls how everything changes. And in particular, the acceleration changes by a formula which you can easily derive. But, and this is the first amazing fact about conformal geometry, and the formulation I'm about to give you is due to Paul Todd just 10 years ago. But the notion itself is due to Yano a long time ago, 1955. Okay, so let me just, before I give you any more formulae, I'll tell you that the definition that Yano gives in 1955 gives you curves on a conformal manifold with preferred parameterizations. the formulation of Paul Todd gives you curves, but without the parameterization. So let me now describe how that goes. Okay, so how it goes is when you first see this, a total mystery, you define this modified derivative of the acceleration. Okay, so there are actually words in the English language for, well, velocity, acceleration. The next thing, derivative acceleration in English, is called the jerk. So this I'm defining this thing to be the modified. This is just some curvature correction terms here, which initially look quite complicated. This is the pretty much the derivative acceleration. And after that, there are more English names like John's or Snap, Crackle, and Pop. Anyway, so this thing here, this mysterious tensor here, which is not a P, it's actually an uppercase rho. So that's a Greek letter rho. It's like the Ricci tensor, which is why it's sort of called the rho, but it's a trace-adjusted multiple of the Ricci tensor. So this is the ordinary everyday Ricci tensor, RAB. I've modified the trace in a certain way, so R is the scalar curvature. So very convenient constants to put in there, and then you modify the whole thing by this 1 over n minus 2. This also, when you first see it, looks mysterious, but there are good ways of saying what rho is without relating it to the Ricci tensor. Anyway, this thing here is called the Schouten tensor. And amazingly, now this is the amazing thing, if you rescale the metric, and remember when you rescale the metric like this, all of the new tensors that I obtain by exactly the same formulae by using the new metric, so the new derivative acceleration modified in this way changes in a really, really nice way. It only scales. Okay? No derivatives, right? So you'd expect, I know, second and third derivatives of omega in here, but there are none. It all washes out. So this curvature and these other correction terms are carefully designed so that everything cancels. And if you do this, even if you're pretty good at, I think I'm reasonably good at sort of messing around with formulae and stuff, it still takes me to derive this from scratch. It still takes me a couple of hours, right? So it's a remarkable fact. But the consequence is this. If you specify that this thing be 0, then it doesn't see the scale at all, right? So this j is 0 is just as good as j hat being 0. And so it's, well, what is it? It's an ordinary differential equation. Like the equation on geodesics is a second order differential equation. You've differentiated one more time, so this is a third order ordinary differential equation that defines what? It defines some curves. And they are conformally invariant, but not parameterized, because the parameterization here is artificial. I've chosen it to be basically to be arc length parameterization. Okay, so forget the parameterization. This gives you some unparameterized curves in conformal geometry, which, as it turns out, as of this year, basically, are useful, just like geodesics are in the Riemannian case. Some people indeed call these curves conformal geodesics, but they're not actually minimizing anything, so I don't really approve of that terminology, but there you have it. You need n to be greater than or equal to 3 here, strictly speaking, because you need this Schouten tensor to make sense. Later on, we'll drop that a little bit. Okay, the terminologies I prefer for these curves is conformal circles. The reason for that is that if you look at this remarkable differential equation in flat space or on the sphere, as a special case of this conformal invariance, you should notice that the sphere and the plane are conformally equivalent, right, by stereographic projection. So there's no loss in looking at curves in the plane, where you just eliminate all of these curvature terms, Schouten tensor identically 0, or when you do it on the sphere. Right, but let's do it on the sphere. So here is the best viewpoint of the sphere from a conformal point of view. You look at the group, this is my notation for the connected component of the identity of the Lorentz group SO n plus 1, 1. So if you look at that and you let it act on Rn plus 2 in the usual way, and therefore on the corresponding projective space you find there are 3 orbits. Okay, there are 3 orbits for this action of this on this homogeneous, otherwise homogeneous space. So there's the sphere. That's where the length of these vectors is 0 according to this Lorentzian metric. There's the inside of the sphere and there's the outside of the sphere. Those are the 3 orbits. But in particular, you can see the sphere sitting there, Sn. Right? And the way that this group acts on the sphere is conformally. This is a very famous thing in physics, how all this operates. And if you look at these curves from this viewpoint, in other words, the solutions of this differential equation, you find that they are circles on the sphere, by which I mean ordinary round circles, not necessarily great circles. In other words, what these things are, in this picture, they are precisely this picture intersected with a 2-plane. So this is a copy of RP2 sitting inside RPN. Use that to slice the sphere, and either what you get is nothing, because this curve might miss the sphere entirely. It might just touch the sphere at one point, or it might cut the sphere, in which case it cuts it in a round circle, just like that. Right, so you deduce that, for example, the moduli space of solutions of this differential equation is exactly the space of circles, which is captured by hitting this thing with a plane. Okay, so the space of 2 planes inside Rp n plus 1 is the same as the space of Grassmannians of 3 planes inside Rn plus 2. And let's just to make sure that we're all on the same page here, I'll do a dimension count to make sure that everything is working out correctly. Okay, so you're expecting the moduli space to be an open subset of this space, which has dimension 3 times n minus 1. So let's see how that happens with the differential equation. Okay, so for the differential equation, you're on a sphere and you're starting at any point on the sphere. So the initial condition is you're starting with a point. N degrees of freedom. That's choosing your point at which you're going to start this curve. Then you have to pick a direction in which to start it. Okay, that's a direction these are like the initial conditions for such a differential equation. Right, so this is like n minus 2 for the dimension of the sphere. That's the round sphere in the tangent space, the unit sphere in the tangent space. Okay, and then you have to specify some additional acceleration, because this is an equation on the derivative of an acceleration. So, and the acceleration could be anything provided it is orthogonal to the initial direction. Okay, so this one here is, could even be 0 here. The 0 acceleration is perfectly acceptable, but it's something which is orthogonal to the original direction. So that's another n minus 1. Okay, so that's exactly how many degrees of freedom you need in the initial conditions in order to specify a curve. But you've overcounted, because what you've got in this way is a curve with a point on it. Right, so if you remove the point, I'm going to remove 1 from my parameter count, then I get 3n minus 1, which is correct. Okay, but, you know, an example, a good example, although I'm cheating a little bit because I said I was going to take n to be greater than or equal to 3, and here I'm taking n to be equal to 2, is that the moduli space, when n is 2, of course, you can think of this sphere, the conformal sphere, as the Riemann sphere. And so the natural group of conformal motions of the Riemann sphere is this group. And so you have this group acting on the Riemann sphere, and if you have something which preserves a great circle, well, SL2R preserves a great circle, divides the sphere into northern hemisphere and equator, and southern hemisphere, and all great circles look like that. So the moduli space of all possible equators is equal to this 6-dimensional Lie group modulo this 3-dimensional Lie group, which is 3, which is what happens when n equals 2. So that's another check that everything is working correctly. But the main question, and this is where parabolic geometry actually has something to say, is, and some representation theory has something to say and so on, is how do you get that ridiculous equation up there, the equation star, star, star? I should be able to derive it in a way which has nothing whatsoever to do with anything, just pure thought plus calculation. All right, so let's try that. So now we're going to go into a little bit of representation theory to see how this happens. I'm just going to tell you things about what you already know, but I'm going to tell you about some elementary homogeneous spaces and homogeneous bundles. Okay, so we'll rip through this quite quickly. So I just want to have a slightly new interpretation of some of these homogeneous bundles. Okay, so suppose you've got any Lie groups, any homogeneous space like that. No special structure, not Riemannian, anything. Just G mod H for any Lie groups G and H, and you have a finite dimensional representation of H. I'm only myself really comfortable with finite dimensional representation. So here we are. E is a finite dimensional representation of H. Then you can build from that a homogeneous bundle. So I just do the usual thing. I take G, the group. I take the Cartesian product with E, and I mod out by the usual relation. And I still get something which has vector spaces of fibers sitting over G mod H. Naturally, G acts on this gadget. It acts on the bundle E. And conversely, if you have such a thing where G is acting on E in a way which is compatible with the way that G is acting on M, you can simply look at the fiber over the base point of M and pick up back this finite dimensional representation, E. Right, so all that is clear and well known. But if E happens to be a representation of G, restricted to H, okay, then you can unwind this construction a little bit in a way which is sort of slightly cheating, but then will restore this. So you do this. So what you can do is just build an isomorphism between G cross E and G cross E by just taking one of the first element G and having it act on E. Right, something which is illegitimate unless E is actually a representation of G. And when you do that, you find that this induces, at least as bundles, but not as homogeneous bundles, it induces an isomorphism as smooth vector bundles between this, which is a homogeneous bundle, and simply the product, right, the product bundle. Okay, now of course this is a little bit cheating. The way that it's really cheating is you've chosen a base point. Okay, in order to realize your manifold N as G mod H, you really have a base point in order to do this. So you want to sort of free that up from this choice of base point. And what the best way of saying that, better said, is that what really happens is that this bundle is equipped with a canonical flat connection. Right? It's equipped with a connection in a way which is invariant under all of your choices. So it's a homogeneous connection, okay? And it's flat, which means that you can use it to trivialize the bundle like this, okay? This is like, if you were just doing this from a more standard point of view, you'd say, well, G over G mod H, well, G has on it a canonically defined one form called the Marocaitin form, which has values in the Lie algebra of G, and then if you have a representation of G, you have a representation of its Lie algebra, and so on, and put this thing together, and you'll get yourself this canonical flat connection. Okay, so this is what you get. All right, now, having had that little interlude and just that small observation on what happens if you have a representation of G, you're inducing from a representation of G, then you can go back to conformal differential geometry. All right? So, first of all, in general, of course, the best representation of G is the Lie algebra. So what you can do is you can build the bundle which is over G mod H, which is the representation of G acting on the Lie algebra, so the adjoint representation, build this homogeneous bundle, and then if you like, you can extract from that more familiar bundles like the similar construction where you take G mod H. G mod H is, of course, not a representation of G. It's a representation of H. Okay, but this one here has a standard geometric interpretation on the right-hand side. That's the tangent bundle. So, in general, this bundle here on the left-hand side, which has a flat connection according to the spiel on the previous slide. This bundle with a flat connection projects onto the tangent bundle. And let's see how this happens on the conformal sphere. Right, and you can see that this has got something to do with parabolic geometry because the stabilizer of a point there is now a parabolic subgroup. And this, what I'm about to say, generalizes to any, more or less, any G modulo a parabolic subgroup. Okay? So what you can do is you can realize this, which is just an abstract construction, you can realize it as happening on the unit sphere, because the unit sphere is a perfectly good model of the sphere. It's just not the conformal sphere. What you've really done is chosen a metric in the conformal class in order to think of it as the root unit sphere. The effect of that is that this bundle here, which is a priori actually only filtered as a vector bundle in an invariant way, actually just splits up. So what you're doing is taking the adjoint representation of SON plus 1, 1 and just restricting it to SON and seeing how it splits up. And what happens, it splits up into 4 pieces. This is reflected on these bundles. So you've got the tangent bundle, which is there already. You're expecting that one. You have the cotangent bundle, which is naturally actually just a sub-bundle, but here it's split up. And then in the middle you have a trivial bundle, and you have a bundle which is modeled on the Lie algebra of SON, which of course you can think of as 2 forms. And then after some turmoil, you can write all this out in terms of the round metric on the usual sphere. Okay, so what you're expecting now is a connection on this bundle, which for the moment you can just think of as 4 separate sub-bundles all put together in a particular way. You have a 1 form, a vector field, but of course you have a metric, so it doesn't matter. This is equally well right. This is a 1 form, it's a unit sphere. This is another 1 form. This may as well have both of its indices down, in which case this is a skew tensor. So it's a 2 form, and then you have a scalar. And you can work out what this connection actually is. And after some turmoil, you'll find the formula for it. Okay, it's a little bit daunting when you first see it, because all I'm doing is taking something which is completely obvious from an abstract point of view and just writing it down in terms of the metric on the unit sphere. So for example, you can see that if I were to set this, and this equal to 0, then all you'd be left with is this first line, which is just the Levi. Now this on the right-hand side, this is the round Levi-Civita connection on the round unit sphere. Okay? Whereas if you bring in some more of these things, you find that bits of this first gadget here feed into the second line and so on. Okay? So it's a little bit awkward, but you can check just to make sure that this is a flat connection. I just compute its curvature, see what it is. It's 0, surprisingly. Okay, now why is this such a good move? Right, so you might think things are getting more complicated here. But the point is that this actually is something which not only works in the flat model of conformal geometry, which is this homogeneous space, but you can check that it actually just pertains more generally. Okay, so this is the content of the next slide. So this is like a curved version of this. So there's no homogeneity anymore, no groups acting. You just have a conformal metric. Everything described locally. Okay, so what you're going to do is take a metric, arbitrary metric in Riemannian geometry, conformally rescale it this way, and try and build something which looks like the previous slide. And the first thing you can do is you can actually figure out, and this is not guesswork or anything, this is again just a computation. You can figure out how all these various gadgets change if you change your metric in this way. So I said that on the previous slide we were starting with the unit metric on the round sphere. Suppose you start with something else on the round sphere, but it happens to be conformally equivalent to it. Okay, so a conformally flat metric. So you should be able to figure out how all these gadgets change. And they change in a nice specified way. So you can see, for example, that the projection to the tangent bundle, which remember is represented by sigma here, is invariantly defined. But when you change this, this conformal metric, you'll find that you are obliged to feed some sigma into the second line. And the way it feeds in is exactly to this formula. And then when you look at how the third line changes, it changes actually in an even more awkward fashion involving quadratic expressions in upsilon. But actually, this calculation is completely mindless. I'm just telling you that this is the result. Right, but even now, you can define a bundle on a general conformal manifold. It has a name, and it's called the adjoint tractor bundle. Okay, so it's, here I've denoted by script A. Okay, so tractor has something to do with, vector, spinner, twister, things like that. I mean, it already exists as a word in the English language, but, this is a new meaning for tractors. Okay, so it starts with some, and I've written it out as a sort of filtered bundle here. It has a projecting part, which is the tangent bundle. It has the one form sitting inside it. It has the two forms and zero forms, and they all feed into each other according to this explicit formula above. And then, after more turmoil, right, now this has got some extra yellow lines in it, meaning that this turmoil here is not just a matter of computation. This is some inspired guesswork, if you like. The point is that you can write down a formula which specializes to the previous formula on the previous slide by replacing all of the occurrences of the metric, GAB, with appropriate combinations of this fancy tensor rho, okay, this Schouten tensor. And then you can check once and for all, and this is actually relatively straightforward if you keep a head straight. It only takes about a day, this one. So you can check once and for all that this is actually a conformally invariant expression. Right? So what you've got to do is make sure that if you apply this connection and then change the metric according to that, and you work out how the Levi-Civita connection changes and so on, and you use that formula up there for how all of these individual constituents change, everything just cancels out. It's really good. But you have to do this, the point is you have to do this calculation once, and then you have the basic tool of conformal differential geometry. Okay, so just to reiterate the conclusion, there is a conformally invariant, what I'm calling a tractor bundle with a tractor connection. So it's a differential operator from sections of, starting with sections of A, ends up with one forms in tensor A, but it's conformally invariant. Shock horror. Okay, now, quite amazingly, this, which is for conformal geometry, pertains in many other geometries. So just in case you know about them, it pertains in CR geometry as well. Okay, and these connections have names. That one's called the Chern-Moser connection. And it also, there are many other examples. We'll get to that later. Right. But once you've got a connection on a bundle, there are some consequences of it. The first consequence is that you can work out what you should do. Anytime you come across a connection, you should work out its curvature, see what it tells you. And this curvature gives you, essentially, in dimension 3, it gives you the Cotton tensor, and in dimension 4 and above, it gives you the Weil tensor. So in other words, this curvature is 0 if and only, for example, in dimension 4, this curvature is 0 if and only if the Weil tensor vanishes. So that's Weil tensor is a well-known conformal invariant. Right? But the way it's usually introduced is you get the Riemann tensor, you break it up into its irreducible parts according to the metric, and then surprise, surprise, one of them happens to be conformally invariant. But here, that one of those parts just falls out as being conformally invariant because it is constructed in a conformally invariant manner. Once you've accepted that this tractor connection is conformally invariant. And not only that, but you can go back the other way. If the Weil tensor is equal to 0, you can use this construction to define an isomorphism locally between your manifold and the flat model. In other words, the Weil tensor is exactly the obstruction to this thing being conformally flat. So you can get many of the classical results just by this simple observation. But the other thing, and this is what I wanted to describe here, is that you also get the equation of conformal circles out. So let me describe how that goes. Okay, so conformal circles are built on ordinary everyday round circles, either in the plane or on the sphere. Okay? And this, this bundle here, this adjoint tractor bundle, is based on the adjoint representation of the group of motions. And of course, you can think of this, this adjoint representation, you can think of its elements as actually being just conformal vector fields on the plane, if you like. Okay, so so these are conformal killing fields. Okay? And so, if you have something like a circle is going to be preserved by some of those fields. So, for the example of the equator on the sphere, be preserved by the Lie algebra of SL2R sitting inside SL2C. And so what you can do is you can pick up a subbundle of the bundle of adjoint tractor bundle by looking at those things which, if we were talking about the flat case, would be just symmetries of the ordinary everyday circle with a particular velocity and a particular acceleration. Right? So after a bit of figuring out, you can find out that that is the right subalgebra. I'll do a dimension check in a moment to make sure that that subbundle has the right dimension. Okay, so this is the subbundle of adjoint. This is a subbundle of what? It's a subbundle of the adjoint tractor bundle, and let's just consider it along this, this curve here. So this curve here gives rise to a velocity and an acceleration, which are fed in by telling you what u is and what and a restriction on f. And then everything else is determined by an arbitrary choice of kappa and phi. So these are functions along gamma. Okay, now let me just do a dimension check to make sure this all works out. In general, this restriction on f in terms of u and a, in terms of the acceleration and the velocity, is a linear vector space of dimension n-1 times n-2 over 2. The point is that, like, for example, if we were looking at the case n equals 2, f would actually be completely determined by this. F would just be the wedge product of u and the acceleration. Okay? And so there'd be no freedom at all. More generally, you can take f to be that, plus anything which is a symmetric form, like in the orthogonal direction. So that's the dimension of the orthogonal Lie algebra in the complementary direction. That explains that n-1, n-2 over 2. And then otherwise, you have three parameters here. You have little f, you have kappa, and you have phi. So this bundle is a bundle of dimension, this, right, plus 3. So it should be that if I look at the space of conformal circles in the plane, well, in flat space, what it should be is a dimension of the big symmetry group, which is this, minus the stabilizer of any particular circle. And if you work that out, it's the answer we had before. It's 3n minus 1. Okay, and now here is the punchline is that you've got this subbundle of this invariantly defined bundle. And you would like to ask a conformally invariant question of this subbundle. And that will give you some restriction on the curve. And what you do is you ask that this subbundle be preserved by this connection that we found just along the curve. Okay, so this formulation is due to, well, they do it in a sort of principal bundle way, but Boris Dubrov and Wojciech Zadnich some years ago. Okay, and when you do that, you'll get this funny equation out. You'll get Paul Todd's equation. It's really quite surprising. I'll just briefly indicate how it works in dimension 2. So in dimension 2, where f is just fixed by u and the acceleration, and this one of the terms in the bottom line is actually proportional to u, so you can absorb that. Then what you're doing is actually looking at this bundle. So here is this three-dimensional bundle when n is equal to 2. So f, phi, and kappa are unconstrained. Then you work out what this derivative actually looks like according to the formula. This is all completely mindless. And right away, you see that this object j, which is this complicated expression, just appears by dint of this doing this. All right? And from there, you can easily deduce the equation, the Paul-Todd's equation. Okay, so that's good. You can do an equivalent calculation without such complication due to myself and Lenka Zalabova, which published this year. But now let me tell you about something which has happened this year, which is really, really good. So this is breaking news. This is an archive article by Peter Cameron, Maciek Donatsky, and Paul Todd. So you might think, what good are these conformal circles? And the answer is that they're more like geodesics than you might think. Okay? And in particular, they cannot spiral. Let me draw a picture of something which might be going wrong if you didn't have this result of Cameron, Donatsky, and Todd. It might be that there's a point on your conformal manifold where geodesics enter any neighborhood of the point, but never reach the point itself. Okay, so I've drawn it sort of symbolically like this. This is something which might happen for these conformal circles. It doesn't happen for geodesics. That's why it's one of the reasons why geodesics are so good in Riemannian geometry. In fact, geodesics for any connection have this property that they cannot spiral. But these ones, they might spiral. Okay, which leads me to another sort of curve. And I'm just going to describe this in 2 dimensions. Okay, so someone recently asked me at a conference, this is why conferences are so good, they asked me about some question about conformal circles. And I foolishly said at the time, well, conformal circles are the only example of these curves which are conformally invariant. Well, that's false, even on the sphere. Let me describe why that's false. So in other words, even on the sphere, conformal circles are not the only conformally homogeneous curves. They're not the only curves, say, locally on the sphere, which have the property that you can get from any point on the curve to any other point on the curve by a conformal transformation whilst preserving the curve. Right? There are other examples. And these examples are well known in navigation. These are called loxodromes. Right, so this is the ordinary sphere, as in the Mercator projection of the sphere. And here is a curve. You can see it exits this side of the map and appears on the other side in the usual way and keeps on spiraling. And so this is of course just a finite portion of the Mercator projection. The Mercator projection goes on forever that way and goes on forever that way. This curve will never reach the North Pole, and it will never reach the South Pole. But in between, it's a curve of constant bearing. Right? So these are historically extremely good curves because you can try and sail along them without getting lost. At least that's the plan. You don't have to know anything about longitudes to be able to make a constant compass bearing on your ship. Okay, when you look at it under stereographic projection in the plane, it looks like this. Okay, so these are some curves in the plane which have the property that they are invariant under Möbius transformations in the plane. Okay, they have an invariant because this bearing here is a real number, and actually they have a discrete invariant as well, because quite surprisingly this sort of thing spirals in the same sense at this point as it does at this point. They're both, if you like, right-handed spirals. They look the same at both points. So let's call this a right-handed loxodrome. And this is viewed in the on the plane. But otherwise, there's this continuous parameter, which is the bearing of this curve. All right, so formula is, once you've realized you should write this out in complex numbers, the formula is straightforward. Beta here is the bearing. This is an arbitrary curve running from point P to point Q as theta runs from -infinity to infinity, and it goes through the origin. Okay, so it's actually a formula which has really 3 free parameters, because you can put the origin anywhere you like, but 3 complex parameters, so it's 6-dimensional space. But it's got a special point on it, the mark, the origin. So it's really a five-dimensional space. So there's a five-dimensional parameter space as compared to a three-parameter space for the circles. This is a complete classification. I don't actually know what happens in higher dimensions. Okay, this is very embarrassing. So you know, in 2 dimensions, if you ask what are all the homogeneous curves on the Riemann sphere, it's either loxodromes of a fixed bearing or it's circles. You know, in 3 dimensions, of course, you can still have loxodromes because you can cut with something lower dimensional, but you can have other things too. But I'm not quite sure how to classify them. But anyway, you can figure out the symmetry of this if you just differentiate this expression. You find you have a particular parameter. Sorry, a particular you get this, which is defined in terms of itself. What that means is that this vector field here is a conformal symmetry. And just by this dimension count, which I did earlier, it's the unique conformal symmetry up to real scale. Okay, so the conformal symmetries of the sphere are all given by quadratic polynomials times d by dz. So here is one of them. Okay, and the general one can be put into this appropriate form by choice of P and Q. So a complete classification. Right, so a tiny bit more of algebra is that, of course, the only invariant of a quadratic polynomial, you know, a binary quantric, is the discriminant. If you work out what the discriminant is in this case, it's that. So all of these P's and Q's cancel out, as they must. And so up to real scale, you may as well just take, say, the real part of this and just divide it by, well, a half the imaginary part. You'll get beta over 1 minus beta, which is perfectly equivalent to the bearing, right? So if beta is a positive number, that's equivalent to specifying that this invariant be any other positive number. And then you can, you know, by what I was saying previously, you can work out how these curves persist in conformal geometry, in curved versions of the flat model. So now all of this was in 2 dimensions, and it's even a little bit complicated if you take a general bearing. If you take beta equal to 1, that means you're looking at loxodromes which are hitting all of the equators and their translates at 45 degrees. These all actually have a classical name. So in the computer, in the compass, north, south, east, and west are cardinal directions, and halfway in between is called an ordinal direction. Okay, after a lot of turmoil, you can work out how to lift the symmetry algebra to the appropriate bundle. Okay, and you find that the gadget that you get here, kappa, is almost invariant, but this thing here, you then get a conformal, well, actually a Möbius invariant equation now. This Möbius invariant equation looks like that, but it involves derivatives of derivatives of derivatives of acceleration. So this is a 5th order ODE. Anyway, this sort of thing will happen on any in any general Möbius geometry in dimension 2. Okay? Right, so I've said enough about that, and let me just tell you say a few words about general parabolic geometry. General parabolic geometry is a sort of quite a big industry because there are many, many interesting cases. What I've been discussing here is conformal geometry, which is, from a Lie algebra point of view, it's either the Bn series or the Cn series, modulo the parabolic subgroup, where you take just one node and remove the corresponding negative root. Okay, so either that in the odd dimensional case or that in the even dimensional case. So all of these parabolic geometries can be encoded into marked Dynkin diagrams like this. Notice in Peter Sonberg's talk he had these two at the start for spin representations and for recording invariantly defined differential operators between these various bundles. And he also had the Cn series and the AN series anyway, but let me tell you about two others. These are really interesting geometries in dimension 5. Okay, and they're sort of classical in the sense that they go back a long way to classical people. Here's one which is, from the Lie algebra point of view, now we all know about G2 and so on. We can just say it's G2 modulo this parabolic subgroup. Okay, what Engel did in 1893, this is just before people really believed that G2 actually existed. Okay, so the title of his article is something like, look, there's a 14-dimensional interesting algebra. Okay, and he writes down an exterior differential system for this algebra, its symmetries of it. And this is also the basis of another differential geometry. You notice the cross is in a different place, another 5-dimensional geometry. This is one of the most intriguing and famous examples of a differential geometry which is not Riemannian geometry. This is the geometry of two planes, two rank 2 distributions, so 2-dimensional subbundles of a 5-dimensional geometry. Okay, so the differential geometry associated to such a gadget is either called a 2-3-5 distribution or Cartan's 5-variable geometry. And associated with this, there are bundles, there are curvature. Not at all obvious, when it is that such a gadget here is actually isomorphic to the flat model, but in principle you can work it out. And Cartan did work it out in 1910. He did not actually come up with what is now called the Cartan connection for this gadget, but he did an equivalent Cartan equivalence method to figure out when such a geometry was flat. But there are heaps of these things, lots more. Okay? If you want more, you look in the big book by Jan Slovak and Andreas Chap from 2009. It's ambitiously called Parabolic Geometries Volume 1 or something like that. And Chapter 4 is called A Panorama of Examples. There are heaps of these things. Okay, that will do. Happy birthday.